plenary talk of today. Roberto lost his voice, so he asked me to jump in. So the next speaker is Luc Devroye. Devroye? Okay.
Yeah, thanks, Gabor. So, in life, to have a good life and to go through life, you need principles. You know, you have a principle, then you know how to vote, how to do this, how to make decisions in the city. So the question is, where do you get your principles? I mean, how do you get them? I get some of my principles from a place, it's on the web. It's called the Urban Dictionary. I don't know, this is sort of the American slang place, but it describes the lowest form of life in the United States. And I asked about, forward is this, right? About mathematics. And this gives you a sense of what it is about. Users put in definitions. It underpins physics, which underpins chemistry, which underpins neuroscience, which underpins the incurable romantic attraction I feel for Beyoncé. Okay, so clearly not a mathematician, but some of it, most people in the world actually hate mathematics. They really hate it, and including this one. Okay, I will not read it out loud. But basically, but the next definition, because people upvote, it's like in Quora or the others, all these places that are similar, you get upvoted or downvoted. And the next one is definitely from a mathematician, and this is basically describes what we're all like, right? We all like doing it, but if you get stuck, you get depressed. So I'd like to thank the organizers for the invitation, but now that I'm on Urban Dictionary, we can find out who are they. Do we really know Roberto? So here is the definition. And listen, it's not me yet, it's Urban Dictionary. It's random, it doesn't make sense. They like hype beast stuff, they vape, they get bad grades, and they have big holes in their socks. Okay, really random. I got luckier with Gabor. Gabor was easy. Gabor is this. Gabor is totally badass. He's the most charming, sweet guy in the entire world. He has the ability to sexually arouse anybody of any gender by just simply walking into the room. Who's that fellow over there? I'm not sure. I would gladly bear his children. He must be Gabor. So these are the two guys that I'd like to thank for the invitation. But let's get on with the main thing. This entry, which I didn't write. I'm sorry. I did not write this. But I will not read it. Otherwise, we're fine. All right. So the title of the talk is Into Amazonia. If you're going to give a talk in Brazil, which has more trees and more kinds of trees than anywhere in the world, you should talk about trees, right? So this is the place. I don't want to make the people who talk about grass feel bad, but you should talk about trees. And so this is the title of the talk. So there was a mention of uniform random recursive trees yesterday. And so I'll go back and remind you of this. Well, this is Amazonia. This is a guy, sorry for this picture. This is a fish called payara. You think piranha is bad. Look at the teeth on this guy. The owner or the fisherman has had a good helping of ayahuasca. If you don't know. You know what ayahuasca is? Others, look it up. There are some ayahuasca clubs in Rio. So uniform random recursive tree is one where you start with a root node, and the root node is labeled 0. And then all the other nodes will be labeled from 1 to n. And the ith node, or the nth node, let's say, connects to a uniform number between 0 and n minus 1, which is the same thing as saying you take n times a uniform. I use the notation capital U for a uniform. You take n times a uniform, truncate it, and then You have that. That uniform will come back. All the notation U is for uniform on 0, 1 throughout the talk. So for example, 3 is shown on the right. 1 connects to 0, of course, but 2 can connect to 1 or 0, and so forth. You choose your parent uniformly. There are n factorial of these trees, easy to see, right? Because you have n choices. The first node has only 1 choice, the second node has 2 choices, and you have n factorial of these trees, and you could say that the nth node has a depth. Depth is the distance from the root. Has a depth that is described more probabilistically by taking n times a uniform, truncated, times another uniform, truncate again, times another uniform, truncate again. And you do this, and the first time you reach 0, that is when you stop, and that is actually the depth. That's the number of steps you had to take to get to the root. And the height, which I will mention frequently today, is the maximum depth. So the talk will be about this and some properties. I won't go too deep into things. And then I will talk about related trees and more recent research, not just by myself, but also by others in here. Okay? So let's move on. Oh, yeah. Listen, it's one of my principles, is that you can steal from other papers and others. My bad luck is that this was stolen from someone. He happened to be here. Igor. Where is Igor? Igor Korczewski. But he said he wouldn't mind. So this is a uniform random recursive tree for 15,000 nodes, just to give you a view of this. A question asked yesterday, I won't go into that today, is that if I show you the tree like this, where is the root? And can you find the root? I have something in pink there. I think it may be there. You know, this is an interesting question to ask. I think I have a couple more. 50,000. Wow. 5,000. So this is graphic by Igor. I prepared this slide before I knew he was coming, so to give the credit. So good. So one way to look at it, so I'll give you a few ways to look at these trees so that analysis becomes easy and proofs are short. And one way is by looking at a relationship with random permutations, uniform random permutations. So if you have a tree where n is 12, as in the example, you can take a uniform random permutation and take a two-dimensional view. So I can just plot I plot sigma 1 at 1, sigma 2, sigma 3. And so you have basically a matrix, an n by n matrix, where you put 1 dot in each row and each column. All of them equally likely, that's a random permutation. So here is another way of, an equivalent way of looking at a uniform random recursive tree. So you take the first node, the node at 1. 0 is the root. And I put a dot at the root at the bottom left corner. And then you take the first node, and that connects to 0. There's no choice. But from there on, that you only connect to the one that is below you. So in this picture, you see an orange region and a greenish region. The first node splits everything in the bottom part and the top part. This will be as follows. So everybody in the bottom part will be in the subtree of 0, subtree of 1 excluded. You understand? And the subtree of 1 is in the greenish part. So any node, the numbers of the nodes are shown in the picture with the permutation. Any node in the greenish part, it will be in the subtree of 1. Right? These will be the nodes 3, 5, 4, 11, and 12. And so forth. So this is totally equivalent to the construction where you pick a random index for your parent. But this it gives you two-line proofs for most of the properties. For example, what is the degree of the root? Can we see the degree of the root from the picture? Well, the numbers are 1, 2, and 10. And if you look at the permutation, it's when in the permutation when you have a record on the low side. 1 sets a record, 2 is the first one that beats it on the low side, and then you have to wait until 10 to beat that, right? And these are the ones that connect to 0. I hope you see the construction, right? 2 must, as a parent, has 0 as a parent. 9 has 2 as a parent, right? You take the one below you that you can see first. Okay, so the degree of the root is equal in distribution to the number of records in the sequence of IID and IID numbers. So it's distributed like the sum of Bernoulli's, 1 over I going from 1 to n. So the average is the harmonic series, so it's log n. But then you have the variance for free, since the Bernoulli's are independent, so you have a representation of the depth of the nth node as a sum of independent random variables. And so you have everything. You have the law of large numbers. You have central limit theorem in 2 lines. So this should be page 1. If you write a book on this, this should be page 2 or 3 on uniform random recursive trees. But let's look at the number of leaves. L for leaves, the bottom. Number of leaves is about half. And can we see this from the picture? Why would about half the nodes be leaves? Why would that be? Well, you're a leaf if nobody connects to you. Nobody connects to you because that means that you cannot have, let's take number 9. If you see number 9, nobody connects to you. So the next higher up horizontally must be before you. And that probability is a half, because between 7 and 9, I put the dots in a random place, right? So I have exactly half the probability. So it's really, really close to a half. Expected value will be n over 2, and then you take it from there. So you can also have central limit theorems for that very easily. So this permutation representation really gives you already a good start in the analysis. All right, here's another one. This is a structural theorem, which is well known, of course, but if we go back to the root, to the previous transparency, the first node splits everything into 2 sets. And there is the set that is in the subtree of number 1, and then the complementary set. And that set has a distribution that is like n times a uniform. You can see it, right? Because the height of the first point is basically uniform between 0 and 12, right? So you get that for free. So the subtree is in pink there. So n times a uniform, I left out the floor function. N times a uniform is basically the size of the first one. And then everybody else is n times 1 minus a uniform. But on the right-hand side, that includes anybody who's not in the subtree of 1, so it's a complement. So that would be the greenish part in the previous picture. But again, you can split now easily, because it's a recursive definition. You can split each of the nodes in turn, and you get something. So you have a representation of the subtree sizes, n times a uniform 1, n times 1 minus a uniform 1, times a uniform 2, a new independent uniform, and so forth. This is what is called the stick-breaking distribution. So the sizes of the subtrees follow this sort of nice distribution. And then now, for a probabilist, this is heaven, right? You just go and enjoy yourself. So that's a structural theorem, which we will use a bit later. There is a second view, and that's the Apolia-Earn view. Suppose that we already have a tree that has 4 nodes, 0, 1, 2, 3, 4. 0, 1, 2, 3. And we have subtrees. Subtrees are not proper subtrees, right? When I mean subtrees of 1, I mean the subtree of 1 that does not include 3. You understand? These are proper subtrees, but they exclude whatever is in the other nodes. So that's, what I draw there could be called a seed tree. It's a seed. You start from there, for example, or you already constructed part of your uniform random recursive tree, and then you look at the subtree sizes. Well, we know that the subtree sizes go to the beta distribution if you in Apolia-Earn. So what's happening is this. When you when you take a new point and it connects to a parent, it chooses initially each one of these, which you can consider as urns, 4 urns, with each one ball in them initially. You choose one of them at random. All right. Then the next one, again you go to the urn, and again you choose one at random. You add one of the same color to that urn, and the urn keeps growing, right? So subtree sizes are basically like the sizes of these urns at the end of a process. This is called Polya urn process. And we know that they have beta distributions in the end. In this case, in this particular example where I have 4 urns each having 1 ball initially, then it's known that all the limits will be beta 1, 3. Equivalently, and this is also follows from the permutation picture that I had showed you. Equivalently, you can take 3 uniforms on 0, 1. They make 4 spacings, uniform spacings. And these are proportional to the subtree sizes. Well, in law, in the limit. In law, okay? And so you can check for that. So this is different than the stick breaking distribution, right? So this is just uniforms, and you just cut the interval 0, 1. So that's another theorem by another good Hungarian. He was called one of the Martians. I don't know, Gabor, have you heard? He was called, von Neumann was his student. And I've been in the talk in it must have been 83 or 84, and I was in Stanford teaching a course. And Polya, there was a seminar, and out of this world, the speaker said something, and then Polya mentioned, he says, "Oh, I had that in a paper from 1927. Okay, all right, that makes an impression, right? He died in 85, at age 98, I think. All right, so there's another view, and this view comes from the connection with random binary search trees, or also called Yule trees in the probabilistic literature, and the biologists call it Yule trees. So on the left is our baby, uniform random recursive tree, and on the right is a random binary search tree. I'll tell you how this grows. Michael Dermota yesterday mentioned how random binary search trees grow. So forget about the node 0. Actually, I have a pointer. Wow. It's not centered, huh? Okay. Forget about this node. You start with a node 1, and anytime you can add, any place you can add a node, just add it uniformly at random. So in this tree, in this binary search tree, you can add a node here, 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 here. I use different colors for where you can add a node. You pick one of those uniformly at random, and that's where you add a node. And that's how it grows. It's a very natural growth. And it's called the random binary search tree for another reason, but let's just say that we grow it that way. Now, every one of these colored sticks that is hanging from the random binary search tree corresponds to the similarly colored stick in the URT. So in the URT, when I add a node, I can add it as a child, as a first child, or I can add it as a youngest sibling. A first child would be like this. 1 has a first child, and that would mean that here you have a left edge. Now let's take a sibling, like number 2 here, adds the youngest sibling in green, and that would be this guy here. Right, so this means, this connection left means you go to the oldest child in this tree, and oh my, and this, and a right edge means you go to a sibling, right? So you have these 1, 2, 3, 5, right? So again, this node will be a sibling of 4, and so it's the next sibling of 4. So that means if you grow this guy here uniformly at random, then you grow this guy uniformly at random. And this is exactly the definition. Exactly the definition. The tree on the right, I keep hitting the wrong button. This is very much. The tree on the right is like the tree on the left tilted 45 degrees. It's a binary tree. You can study its height by studying the weighted height. So height is the longest distance from zero, the furthest distance from zero to any leaf. But going down in the tree, making a new child, that is actually corresponding to a left edge in this model. And so if we put with every edge a 1 when we go left and a 0 when we go right, and we add up what, these weights, then the height of the URT is the same as the maximum weight node in the random binary search tree. It's a weighted height. And weighted heights, we know how to get to handle them. So it's just a small addition. And so we did that. The height, it turns out to be close to E log n. There's a very nice paper by Luigi and Toyota where they proved that the height is not only E log n, it's a log n tree. The random binary search tree is a log n tree, and this must be smaller in height, so should be some number between 2 and 4.3, but it's the height minus E log n minus some constant times log n. And that's actually tight in probability, so it's order 1 in probability. So it's, we really know the height up to just a small number. Very nice result from 2013. I leave you with an exercise if you're students. The upper bound is relatively easy. The lower bound, it's a bit trickier. There are many proofs, some involving branching random walks, but the upper bound is this. The probability that height is bigger than E log n. That's just no more than n times, because you have n nodes, the probability that n times a uniform, a product of uniforms up to E log n is bigger than 1. Right? We truncate, right? Leave out the truncations. That gives you that, right? So we are here. This is a product of uniforms. Well, this is e to the power gamma. If you know about uniform is e to the power minus an exponential. So this you could say, okay, I leave it as an exercise to prove that this is 1. But if you go here and you say, oh, I'll do Chernoff, no. You will not get, so Chernoff is always beaten by optimizing the power of the kth moment, and you optimize with respect to k. So if we take the expected value of n times the product of uniforms to the power lambda, then you get that second line, right? It is an exercise in Gabor's book on inequalities that doing that is always better than Chernoff. So let's do that. So we have that. So this is a moment version of Chernoff, if you wish. And you optimize with respect to lambda. You get to some expression. Expected value of a uniform to the lambda is 1 over lambda plus 1. So everything is explicit and nice. And you get that this is exactly 1 to the power of 1. So then the exercise is, so this is not strong enough, do this. You'll discover, of course you can do this if you know large deviation theory, but just do it by hand. Don't look at any book. Don't ask ChatGPT or whatever. The fringe. That's where we all live actually, but the fringe. What is the fringe in a tree? By fringe is meant, in the literature on random trees, is meant whatever is close to the leaves. The problem here is, and this will annoy many good farmers, is that the leaves, the root is close to a leaf. Root is close to a leaf. Actually, root is very likely to have a leaf as a child in the URT. So we can talk about patterns. A pattern is a certain form of a tree, right, as shown there. And that already gives us a few nice problems. So one of the things is how many nodes have subtrees of size k, right? How many nodes have subtrees of size k? This is a structural parameter. Really easy. We go back to the permutations for that. So here's the permutation view. So let's look at this node. The subtree size is exactly the number of nodes that are to the right in all the successive horizontal levels. And it stops when you find a node that is killed. The subtree is killed by this node. Right? So that means among all of these k plus 1 values, k plus 1, right? Among the k plus 1 values, this must be the smallest in an x-coordinate. This must be the second smallest. The probability of that is exactly 1 over k plus 1. And since this happens, basically, you can repeat this everywhere. It basically doesn't matter where you are in this permutation view. So basically, the number of subtrees of size k should be n divided by k plus 1. And it's trivial then to get also central limit theorems and so forth. The number of nodes of degree k, I already said what number of leaves should be n over 2, but the number of nodes of degree k is n over 2 to the power k plus 1. Yeah. And so the one other example, so there was been some literature on the maximum protection number. Strange name. That's the minimal distance to a leaf. So if you live somewhere, you don't want to see a leaf within a certain distance from you. And the maximum, well, maybe it shouldn't go, it's not going to be constant. It actually goes to infinity slowly. And it occurs basically because of this. If you have a chain like this, then the nearest leaf will be here, right? If you have a chain. And that's the most likely thing. If you go in degree 2 and you start having below you more than a chain, then it will be more likely to have a close leaf. Well, in that permutation, again, in the subtree, in the permutation view, that means that you need to have a chain like this. Exactly this. This is the subtree, but they must be all to the right, to the right, to the right, to the right. And that has a probability over 1 over k factorial, right? Yeah, these permutations I was showing, a random permutation drawn this way is the same has the same distribution as a random permutation drawn the other way. So, awful. Okay, so, and the inverse of the factorial is log n over log n. If it has to kill the probability of seeing this. So that will be that. And then we came to the maximum degree. And this is really strange when we discovered that the maximum degree is not at the root. And we go back to Igor's pictures. There were several nodes that had high degrees, and actually, if you focus visually on a tree and your eye focuses on the largest degree, wrong in the hierarchy. The largest degree node is actually quite a distance away from the root. So there are about E log n levels in the uniform random recursive tree. And Laura Eslava, who was Luigi's student at McGill, who is now at UNAM in Mexico, she found that the largest degree node lives at log n times a constant from the root. There are many nodes, and then some of them are likely to have, since you have a bigger choice, then some of them, by the exponential explosion of the number of nodes by level, some of them will be more likely to have the high degree there. So if you want to discover where the root was, if I show you the tree, but you don't know where the root was, don't go by the highest degree because you will be fooled. And this is interesting. She has many fine results on this, like how many there are, the joint distribution of the distance and the degree and so forth. It was quite a surprise, and it's sort of annoying for the people doing reconstruction of the route. If the organizers permit me, I will take 5 minutes or maybe 10 minutes to talk about this problem. The largest eigenvalue. So now I'm going to slowly crank up a little bit the level of the talk, but it's still very basic here. So consider the URT as given as an adjacency matrix. Standard stuff for graphs. It's an adjacency matrix. And so then there is an inequality that I will actually prove to you. So the largest eigenvalue is lambda 1. And it is always sandwiched between the square root of the max degree and 2 times that. It's in between. And it's deterministic. There's nothing hidden. That's the truth. And that one can show, several ways of showing it, but one way would be to look at at path counting. So if I take the adjacency matrix to the power k at the position I, j in the matrix, that counts the number of paths from I to j that take k steps. If you take one step, then it's 1 if there is one path, and it's 0 if there is no path, right? So that's the definition of an adjacency matrix. And so to the power k, that it counts the number of paths. So if you take 2k, so I'm forcing the exponent to be even, and you go from I to I, that's actually the number of cycles, the cycling paths that go back to I, right? Good, we're going to count those, and those are important because if you go from I to I, that sits on the diagonal. And we know that property, that the sum of the eigenvalues is equal to the trace of the matrix, the sum of the diagonal elements. So we have the following series of inequalities, and it's relatively easy. I don't know where to start. Let's start here, for example. This is the trace, and that's the sum of the eigenvalues. But eigenvalue of a to the power 2k, that's the eigenvalue of a to the power 2k, right? So this should be a trivial step. And that's sandwiched between lambda 1 and n times lambda 1, right? And here on the same thing here, I don't care about this n. Huh? We may say, oh, why? No. And then here, this is bigger than the max entry in the path counting, and it is less than n times the max. These are trivial inequalities. But now if I take the whole thing to the power 1 over 2k, on left and right, I have a bunch of inequalities here, right? They have these two at the same time and these two. If I take this n doesn't matter anymore. The n just disappears. N to the power 1 over 2k goes to 1. And so here is the thing. So it's the limit as k goes to infinity of the maximum number of paths that go from I to I, cycling paths. Okay, so then we're fine. So now you have a max degree. So I'll show you 2 ways of, I'll just show you the inequality. And here it is. It's 1 page. I should have, I don't know why this is empty, but okay. At the top, there is a high degree node. It has degree delta. The pink node is degree delta. So here's one way we can make a path. So I'm working on the lower bound, right? I'm going to show you at least how many paths there should be. So I start at the root, and then I go down 1, I go up. Go down 1, and go. When I go up, I have no choice. But when I go down, every time I have delta choices. So that means that the number of paths I make in this way, and very restricted, the number of paths I make in this way is delta to the power k. And then I take the power 1 over 2k, and you get it, right? So that's a lower bound. The upper bound is also similarly easy. So I'm showing you on the left a tree, and I start at any node I. Yeah? So now you make a cycle path. Well, the path goes down, but it also goes up. And it goes up. In the end, it must come down to the same level. So if you just look at the movements up and down, that's basically like a walk, right? A walk where you have as many ups as you have downs. You must come back to yourself, right? So that's just the vertical movement. So you must come back to where you started from. And that's it. There's a 2k, for a length 2k path, there are 2k choose k paths. And I don't care if you go out of bounds. That's an overcount. It's no more than. It's an overcount. I don't want a Catalan number. I don't want none of this. 2k choose k. And every time you go up, you have one choice, so we ignore those. Every time you go down, you have at most delta choices. So that describes all the paths. So basically, you can no way that you can have more. So that's the upper bound here. So this is the k choices when you go down. This is the paths. That's basically 4 delta to the k times peanuts. And then you get it, right? I take the 1 over 2k power, and the whole thing is done, right? 2 root delta. So the 2 comes from this path, choosing the path. Good, let's do some examples. Maybe that should work it out. So I have 4 examples here, and then we will be back on track. So the first is the Cayley tree. And this is a recent work by Luigi and Roberto and Bruce. And they showed that lambda 1 in a Cayley tree. What is a Cayley tree? A Cayley tree is a labeled tree. It's connected, and it has labels 1 to n, and all of them are equally likely. That you are on the square root of delta side. You're on the low side. And the maximum degree in these trees is known to be about log n over log n, so you have that result. So you're on the low side. All the examples except the last one are on either the low side or the high side in the 2 bounds. And usually that cuts the proofs that you have about showing the asymptotic behavior of lambda 1, cuts those proofs in half because one side is covered by the inequality, right? For a Catalan tree, now this is a random binary tree on n nodes, all trees being equally likely. There we have a different thing. So there's a nice result by Rojo and Robiano. They're from Chile. I don't know if they have ever. Do you know this guy? There's a very nice paper. If you take a d-ary tree with k levels, as shown here, then lambda 1 is exactly this. It's 2 times the square root of d times the cosine of pi over k plus 1 by explicit computation of the eigenvalue. And so if you find, so this is interesting. So if you have a tree in which somewhere in the tree you find this structure, like a structure where every node has a degree d, and then you make these complete trees, they may be hidden. But in the Catalan tree, you have a binary tree. There are quite a few that even are up to height log n. So these complete trees are sitting in pockets distributed in a binary tree. And then we know that there, with k being quite large, log n, not a constant, and therefore the cosine will be near 1, right? Cosine at 0 is 1. So the cosine will be near 1. So you're at 2 times root delta. So this means that you're on the high side. So the eigenvalue of a tree is on the high side when you find pockets where you have lots of these high degree or max degree nodes nearby. And that's exactly what it is. So the eigenvalue is square root of 8, 2 times square root of 2. Linear preferential attachment trees are well known. These are trees where instead of choosing a node randomly and uniformly, you choose it with probability proportional to 1 plus the degree. And this has been generalized as well, and we know everything about I actually have a picture. Let me see. Yeah, this one is stolen from Curia. And this one has very outspoken high degrees. The root here is much easier to find, even visually. You probably, I'll put my money on the big one there, right? On this one here, that it is the root. I don't know in this case, but it should be like that. There, see, you have this high degree node, but it is not surrounded by other high degree nodes. It's surrounded by nothing, basically. small degree node. So you should be on the low side. So the maximum number of paths will come from actually going back and forth near the high degree node. And that's true. There's lots of things known about that. Bamidi and Evans and Sen have a very nice paper about this. So you're on the low side. And then we come to the uniform random recursive tree, which was studied by the Jobim research group. That one, we are in a first example that I know of, where we're not near the lower bound or not near the upper bound. So that means the high degree node, as we already know, is not surrounded by other high degree nodes. Remember, log to the base 2 of n, that LoRa is lava result. Well, it's just sitting there, but it is isolated. And so what is going on is the following thing. It's trying to explain that result. Is that we know about the subtree sizes, right? So I'm showing you with every node on the left, the subtree size is shown next to the node. So at the root, it's n. N plus, it should be n plus 1, but okay, n. And then you have this stick breaking thing. N u1, n1 minus u1, u2, and so forth. And we already know that the degree is basically the log of the subtree size. And that propagates everywhere. So the log of n so the degree of the node is shown on the right. It should be log n at the root, we know that. And then it should be log n plus log of a uniform, but log of a uniform is like minus an exponential. And so these are not, the exponentials shown on the right are not independent, but this is not important. So you have log of n minus an exponential, then log of n minus the sum of two exponentials, log of n. These are the degrees. So the degrees basically go down like by 1. Log an exponential is basically 1, right? So they go down by 1 and then 2, right? So the degree here is this degree minus 1, minus 2, minus 3, roughly speaking, and so forth. And as you go down, so if I take the fourth child here and then the fifth child of that child, then I have 9 exponentials that I subtract. So this is an interesting structure, and from there you can see that you can start walking, but you have to be a bit careful if you do path counting, because now the degrees are not exactly log n. They go down gradually. You're standing on a slope. Anyway, that's to explain that thing. Okay. I'm going to describe a few other trees. So what if we restrict things? So one thing that we could restrict is the height. We can say, well, the height, we expect it to be E log n. But what if somebody tells us, what about uniform random recursive trees conditioned on the height being much larger than E log n? That will elongate it, and I don't know the answer to that, but maybe there will be new random trees that will appear out of nowhere by just conditioning on things that are rare. One way of conditioning will be, for example, by growing the tree, making it an increasing tree. Increasing means that the labels go down as you go down from the root. You make it increasing, but we make a restriction on the degree. Say the maximum degree cannot be more than d. But we know that naturally, it's in the nature of the uniform random recursive tree to have a log n degree. It wants a log n degree, but you say, no, I deny it. It can be d, right? So you expect the tree to be a bit higher, right? Because the nodes cannot all seek a refuge under the umbrella of the root. So many examples. If you take trees, let's make trees that all the trees are equally likely, but they have to have maximum degree d. There are generalizations that don't matter. Well, then we can also do things. But this was suggested by the French mafia, Bergeron, Flageolet, and Salvi in '92. And they were the first ones to suggest this model, and more general models, and I think Michael Dermota has also published on it, and it's a well-known model. At least for the degree question, things are all known. The height is known, the depths are known, and they generalize what we already know. So if the D goes to infinity, then you have no restriction on the degree. You should get uniform random recursive tree back. And so that's one, so I will not say too much about that. Here's another model that came about very naturally. What about if we don't go to a uniform parent, but we go to a non-uniform parent? So the parent will be n times x truncated, and x is some random variable between 0 and 1. And no further restrictions. Even in that case, one can do the depth and the heights. An example would be that you have two proposal parents, and you take the one that is either the youngest or the oldest by label. You take the youngest or the oldest as your parent. How does that change things? This was suggested by Mahmoud. And that is, if you take the oldest of the two parents, you get back the random binary search tree, but I will not go into that. So that's called a scaled random recursive tree. So all these trees have the following property. So I'm showing you the profile so that you can, so the root is left, and then as you go deeper in the tree, you go to the right, deeper and deeper. At the right, they're all log n trees, so they have log n times a constant, which is lowercase h. And most nodes live near the mean, and the mean is, in this case, this mu is the expected value of log of 1 over x. And now you can have this for any x you like, on 0, 1. And you have a variance. So this is kind of stuff that you have seen in renewal theory maybe. But anyway, most nodes live near the middle, and the width of that bell curve is about square root log n. So these trees look like there's nothing on them, and then all the nodes are basically at the same level from the root, except a few. I don't know what. If you look at the canopy in the Amazon, if you look at the canopy, all the leaves in the trees are about the same level from the root. Huh? There's nothing below because they are in the shade. There's nothing above. But this one has something sticking out. I don't know if there's like a little tower sticking out, but otherwise, most nodes form a nice canopy. So that is what all these trees look like. Yeah?
Outside of the bulk, this power, is it known how, outside of the bulk?
The rate? The rate in the profile?
Yeah, sort of, yeah.
How fast this goes to 0, you mean?
Yeah,
this here.
Outside of the bulk, is this known?
Yeah, the profiles have been studied, not for all these things, but for the regular trees. This is well known. In the analysis of algorithms literature, you'll find this. Yeah. Let me just go a little bit over Fringe. I'll just mention this, as we are running out of time. So this one is with a few, I'm talking a little bit about my own results, but this is a model suggested by Krapivsky and Redner and Saramaki and Kasky some time ago. And it's related to the uniform random recursive tree. Here's what you do. You choose a random parent, and you make one little change, tiny change. You say, I'm not going to connect and be a child of that random parent, but I'm going to be connecting to a uniformly chosen neighbor of that node. It's like only one of. You see, this cannot be substantial. Well, I mean, this is almost like you say, but that's not true. And so Krapivsky, who was in statistical mechanics, posed that question, and then they ran simulations, and strange things happen. I will show you a tree here. So this is stolen from our own paper. And he said, I don't know, Celine is here. Is Celine here? Who made that picture? What? Oui? Ah, Simon Briand. Okay, Simon. So one of the co-authors made it, luckily. You see these, what we call hubs. And this is not a uniform random recursive tree. You immediately see that. And so the number of leaves in this tree is n minus n to some power, which is about less than 0.9. So n minus small o of n nodes are leaves, basically almost every. So what happens is this. You take a random node. It's very likely you're going to take a random node. All these blobs are actually connected to the center of the blob, distance 1. So this is the center, and all these nodes in here are actually all neighbors, but this is the way of visualizing. So you will take one of these, if you take a random node, okay? And then you say, oh, I'm connecting to a random neighbor, but these guys have only one neighbor that is the center. And so then they go to the center and they connect to that, but then that means they make another leaf. And this is like a snowball effect. And so you make these hubs, and these hubs grow. And so we have a bunch of results on that. So this is with Luigi and Simon, who made the picture, myself, Serte in the Netherlands, Celine, who is here, and Bruce. And so the number of hubs is polynomial, but we don't know the exact exponent. The number of leaves is bigger than n minus n to the power 9/10, as I mentioned. The number of nodes of degree k grows also polynomially. So this is really completely different behavior, at least for these parameters, which to me came as a shock in the beginning. And with this little change. There are things that don't change too much, like the height and the maximum protection number and so forth that I mentioned. They are basically unchanged. So this is a very nice picture. I will, okay, last, no, I will not. I think I will stop here. These are just the slides I was going to show, but I will not. But I showed this picture. I like this guy. Back to the Amazon. Happy guys in an amazing place. Okay, thank you very much.
Has this picture inspired any problems about trees?
I just love. Dude, I mean, I've never seen a fish like this. It's just amazing what lives here, right? Anyway, okay.
Okay,
Thank you.